Hello everyone, it's Ollie Epsom and welcome back to our series on offshore wind. This is part 4 of 5. I should make a quick announcement that I apologise for the delay between part 3 and part 4. It should have been a couple of weeks, it turned into a couple of months. It turns out that getting married requires a certain amount of input from Ollie Epsoms, which can be deleterious to the production of videos. Secondly, I want to reiterate the fact that this channel never has been, is not, and never will be monetized. Unfortunately, YouTube is slapping crappy adverts for NordVPN and Grammarly and all sorts of other nonsense over everybody's videos at the moment. Rest assured, not a single penny of that goes to me, so feel free to ad block the bejesus out of it. There are sufficient shill channels on YouTube promoting such things to allow the owners of YouTube to run the servers and live lives of unparalleled luxury without recourse to destroying the good name of this channel. Let's get started. In part 1 of this series, we had an introduction to renewable energy and wind farms. So basically, what types of renewable energy exist, why we may wish to use them, and what advantages wind farms specifically have for certain parts of the world, in particular Northern Europe. In part 2, we looked at the general principles of wind turbines, their main parts, and the architecture of them. In part 3, we went into more detail about the major components, for example, the blades, the bearings, and so on. In part 4, which is this part, we're going to be looking at the electrical layout of the wind farm, which is the largely unseen network of cables under the sea, which transfers the energy shoreside to your home. We're going to be looking briefly at transformer systems, cables, switchgear, auxiliary equipment and control gear. Although, as a caveat, I'm going to say that with the exception of the electrical layout, I'm not going to be going into a lot of detail about these things because I'm fundamentally a mechanical engineer. Although I do know electrical stuff, I don't know it in sufficient detail to start talking about it in this forum. Part 5, the final part, which I hope to release in the next week or two, assuming I don't have to get married again. We're going to be looking at the offshore wind farm layout, so how that layout's built in the first place, how we build the wind farm, and how we operate it. Before we get into the detailed stuff, I think it's probably worth us recapping the general arrangement of an offshore wind farm. So over here on the right, we would have a wind turbine, which when the wind hits it is going to rotate in a clockwise direction as viewed from the front. There's an unofficial agreement amongst wind turbine manufacturers that all wind turbines rotate clockwise. It is a source of never-ending woe to me that the wind farm for which I work employs a logo, presumably from some sort of highly paid PR agency, that clearly depicts a wind turbine turning anti-clockwise. This is incorrect. Having said that, there are some studies at the moment which show that efficiencies of wind farms could be improved if every other turbine turns in an opposite direction, but that's another talk for another day. The wind turbine spins and it generally produces at the generator something like 600 volts DC, which is then inverted and then transformed to something in the region of 33 or 66 kV, depending on the farm. Then it will go through some switchgear and then it will go out the inter-array cable, down the jacket or foundation and along the seafloor through the inter-array cable up until the offshore substation and into another set of switchgear. Now, small offshore wind farms or wind farms which are very close to the shore will not have an offshore substation. They will just have the inter-array cable going directly to land. However, we are assuming we are a big, full-size, important, toxically masculine wind farm, and therefore we have an offshore substation. And the job of the offshore substation is to take the inter-array voltage, which is 33 or 66 kilovolts, and turn it into the export cable voltage, which is typically going to be 220 kilovolts, or on big new farms it might be HVDC of various voltages. Then it will go out a minimum of usually 2 export cables, which are physically in parallel to each other as well as electrically, along the seafloor until it enters a special drilled duct called a HDD, or horizontally drilled duct, which is a protective duct which allows the cable to make landfall at a thing called a TJB, which is the transition joint bay, and that is where the high spec, watertight, super duper, you can't bend it offshore export cable is connected to the less super duper, because it's onshore, underground cable, and that will also go through a horizontally directly drilled channel to the onshore substation, which is usually close by but may not necessarily be. The onshore substation has a series of switchgear and transformers and inductors and filters and so on in it that allows that electricity to be conditioned and connected to the grid, where it flows eventually to your house, where the electric company bends you over for the bill. Because in spite of the fact that wind energy is by some significant margin the cheapest form of energy in Northern Europe at the moment, you can rest assured that that saving will not find its way to your bill because reasons to do with Ukraine or something. But that is the benefit of living in a capitalist society, so we can't complain. Let's take a look quickly at an actual wind farm. This is Beatrice off the coast of Scotland, and the wind farm itself is located in this red zone, and in there you have your multiple turbines, which is 88, and you have 2 offshore substation units, and they are feeding into the export cables which go down this corridor marked in black to a transition joint bay offshore in Bucky, and a onshore substation where it then connects to the grid. Now you may well ask, why not go directly to Wick with your export cable? And the answer is that the people live down here in southern Scotland, and therefore that's where the electricity is needed. If we took the electricity in Wick, we'd have to build an additional line to get that power down towards the south. In addition, there are now additional wind farms being built in the general area, and they are also using export cables which go down to the Bucky region, and there are also additional bootstrapping HVDC cables across the Moray Firth which will allow additional renewable energy to be taken down from northern Scotland in future. So the reason I mention this is just to say that the export cable is usually the shortest possible cable, but when we're building farms in very remote areas, we may take the hit and have a longer export cable, because it means that we have less trouble with other aspects of the farm. I want to spend a brief few minutes looking at single line diagrams, or SLDs. Now, I can't show you a real single line diagram because they're kind of commercially sensitive, so I've had to download this one from the internet, and it's not great, but it will show you the general concepts. What you have in these circles are individual wind turbine generators, and they are connected in strings, which we'll look at in the next slide, to the inter-array cables, which then feed into the offshore substation, where it's shown here that there's 2 transformers and an auxiliary, and that auxiliary transformer will provide domestic power for the OSS. Now, the thing it's not showing you is there will also be a breaker between the output of the 2 transformers, and there'll be 2 export cables, and this one's only showing 1. Now, not only that, but you can see here where the sea cable meets the land cable, there's a transition joint bay, but there is no onshore substation shown. It's just going directly into the external grid. Now, I did say that there are plenty of wind farms with no onshore substation and an offshore substation, but I don't know of many or any where it's the other way around, as shown in this diagram. However, that is the general principle, and for the purpose of what we need to know, this is good enough. Now, a proper single line diagram will show you all the switches, all the breakers, all the line reactors, all the reactive power compensation and so on. This one doesn't, but it does suffice. Right, what we saw on the single line diagram previously was a lot of inter-array cables predominantly. An inter-array cable, its job is to bring power from several turbines to an offshore substation or an onshore substation. Here, in this picture here, is an example of me touching a inter-array cable for Beatrice Offshore Wind Farm. This inter-array cable section was actually on a mock-up of the transition piece that we built prior to building the farm to make sure that everything goes together. You can see it's relatively substantial. Traditionally, inter-array cables ran at 33 kilovolts, 50 hertz AC. Now, that is a traditional voltage and frequency. I know that some people, including our colonialist brethren, do run at 60 hertz. However, they're not in the business of building wind farms, so we can ignore them for the purposes of wind farms. It would, of course, be nice if we could ignore them for the purposes of everything, but unfortunately we live in an interconnected world. Modern wind farms typically run at 66 kilovolts because the turbines are much more powerful and bigger. The disadvantage of 66 kV is that the transformers and switchgear on the turbines themselves have to be physically larger and bulkier, but of course you can save on a cable. So what you lose on the swings, you may gain on the roundabouts, and it depends on the particular layout of the wind farm which voltage you go for, but the trend is very much 66 now. So cables also carry fiber optics for data and temperature measurement. That last one, temperature measurement, is relatively important. We chuck the cables out of the back of a ship, like this generic cable laying ship, and then typically what you'll do is you'll trench that cable at least 1 meter under the permanent sand bed. There's many reasons for that, not least fishermen dragging scallop dredgers over everything. So the cable in practice is surrounded by sand, and because all three cores of a three-phase cable are close together, you do get heating from inductive currents. Now that heat has to go somewhere, and it does go into the sand and eventually the sea, but we do need to monitor the temperature of that cable, and we do that with lasers and fiber optics. The conductors can be copper or aluminium. I mean, in principle they could be any metal really, but copper and aluminium are good conductors, and aluminium is of course cheap. Now copper is a better conductor. You need more aluminium both by weight and volume to conduct an equivalent amount of electrons with the same losses, but because of the cost of copper recently, aluminium is increasingly being used. The cable outside is armoured very, very heavily. Usually, if it's an inter-array cable, it will be with galvanized steel, but with the heavier duty export cables that take more power at higher voltages, the galvanized steel can heat up due to inductive heating. So a low magnetic or non-magnetic alloy or stainless steel is typically used for export cables, or even a composite. Obviously that does make it rather more expensive, so where possible that is not used. The conductor cross-sectional area is in the region of, I've written 1000 to 1800 square millimeters per phase. Actual fact, it's going to be more in the region of 200 to 1800 millimeters squared per phase, depending on what the conductor material is, what part of the array the export cable is in, because we don't necessarily use the same CSA for the whole job. Obviously, as you can imagine, we use the minimum CSA we can, and the layout of the farm and the powers and so on. But anyway, they are quite chunky. The inter-array cable topology can typically be of two kinds, because the cables need to be routed between the turbines and the OSS, and how they do that is dependent on the requirements of the farm and the pockets of the investor. There's two main ways of doing it, which are strings and loops. So a string is the cheapest, lowest cost option, and what a string is if I have my offshore substation, behold the amazingness of my drawing, you will have an inter-array cable coming out of it, and it will go into turbine 1. and out of turbine 1, and then it will go into turbine 2 and out of turbine 2, and so on. And I'm just going to represent them by circles now because it's quicker. And at the end of the string it just stops. What that means is that the power goes in one direction along the string typically, and that means that you can have a string with a big cross-sectional area at the start where the power of, let's say, 4 turbines has to go through it, and then at the end you can have a much smaller cross-section because you've got only 1 turbine going through it. And of course you don't have any additional cable, so strings tend to be cheaper. Unfortunately, however, there is a problem with a string, which is that if you lose a part of the string, let's say that section there, then what will then happen is the entire string is dead. Now that is bad for 2 reasons. One, of course, you've lost 4 wind turbines generation because a fisherman has dragged a scallop dredger through your cable, or a termination have overheated, or there's been an instrumentation fault and you think the cable is trashed and it isn't. 2, you then need to provide power to the turbines which are stuck at the end of those strings because they need to exercise the main bearings, they need to keep the dehumidifiers running, they need to exercise the pitch bearings and so on. So you need to install a noisy great diesel generator on that turbine, and you need to drop that there with a ship, and it needs fuel, and so you need to keep filling it up with fuel, and you need to do that for as long as those turbines don't have power. Now that can be a very expensive job to do, not because diesel generators and fuel are particularly pricey in the grand scheme of things, but because in bad weather it may be a while before you can get to these turbines. So if, for example, the turbine's been loafing around with no power for a while, the first thing the manufacturer is going to do is tell you your warranty is void. So that can be extremely expensive. For that reason, I personally, and most engineers, would prefer to use loops. Now, loops are like what in Britain you would have in a ring main in a house. But again, I appreciate that for many of my international viewers not familiar with 17th edition electrical systems will not know what a ring main is. But basically, it's pretty self-explanatory. If we have another string with 4 turbines on it, so let's call that string A and string B, what we'll do is we'll link the 2 ends of the strings together, and what that means is that in the best case scenario we can export power back that way. For example, if we have a failure here, now the actual degree to which you can export power the wrong way down a string is dependent on how the cross-sectional area of the string works out, because of course you still want to save as much money as possible, and you still do not want to use larger cross-sectional areas than needed. So in practice you are not going to be able to export like a full string load if, for example, you lose the string A right at the OSS. You're not going to be able to get all those 4 additional turbines through string B, but you will be able to get some power. And equally important, you can always backfeed and keep those turbines alive with a little bit of power by backfeeding the string. Now that is the situation that I have always liked and the situation that I have always wanted. However, you will find that accountants, as soon as they see, oh, there's an extra piece of cable here, and why do we need that? And you say, well, it's so that we can operate in faulted conditions. And then the accountant will say, well, why would there ever be faulted conditions? There'll never be faulted conditions on a wind farm, right? They'll always be absolutely fine. And you say, yes, well, they do fail sometimes. And they say, no, they don't. And then they take out the strings and you get a string wind farm. Now, in your early days of round 1 wind farms in the UK, everybody went for strings because they weren't expecting failures. Now, it doesn't necessarily have to be the cable itself that fails. It could be a cable terminator, it could be a piece of switchgear, it could be a control system, etc. And pretty soon cable failures started to occur, and it was realized that these cable failures cost more money than just having loops. Therefore, in round 2 wind farms, you saw a lot of loops. And certainly every wind farm that I've promoted has had loops, but that's because I'm a good engineer. Now, however, we have a better understanding of how to build things. So it is true now that cable failures are not as common, and therefore some wind farms are going back to strings. And I would say at the moment, from the ones I know in development, it's about 50-50. I will always maintain that we need loops, and I will always maintain that that's the best engineering solution. Now, you're probably wondering why I've got a map of America up here with a route shown between various cities, and the brighter amongst you will realise that this is the travelling salesman problem. The travelling salesman problem is a sort of thought experiment which says you've got a guy and he has to go to a range of cities to sell something. What is the shortest route between all those cities? Now, the interesting thing is that if you have, say, 100 cities, then the answer is that there are 100 factorial potential routes between those cities. So if you were to work out every single possible route that the travelling salesman could take between those cities, it would take you trillions of times longer than the universe has existed in order to do it. Why am I mentioning the travelling salesman problem? Well, quite simply because if I have turbines in a farm, and they may or may not be arranged neatly in a grid depending on the conditions of that farm, and I have an OSS and I want to have cables linking the turbines together, then that is a derivative of the travelling salesman problem, and it's actually known as a VRP, or vehicle routing problem. So effectively, if you think of the cable as a lorry or a delivery van that needs to go from a depot to various drop-off points, then that is the problem. Now, luckily for me, very clever people at Google have come up with some algorithms that can solve this, or at least guarantee that they're going to be within a certain number of percent of the optimal solution without taking trillions of times the age of the universe. So I recently downloaded some of this solver code, and it's actually Google that developed it. So thank you, Google. I guess some of the advertising remedy from these videos is useful. And I programmed up in Python a system with a graphical user interface that can take the lat and longs of turbines and the OSS and allows you to select how many strings or loops you want, what power there are, and so off, and it will instantly calculate the optimum cable route. When you run the code, for example, on this hypothetical wind farm, which has 36 turbines, if you give it 8 strings, it will optimize it and tell you that you need 53.2 kilometers of cable. Now, if you did this manually, you wouldn't get anything like that. You'd probably end up getting 60 kilometers. And this is a relatively simple wind farm layout. So if you can imagine, if you had a much more complex layout where the turbines aren't in such nice straight lines, then you can actually get it wrong. With the code, I've also allowed you to specify the individual water depth at each turbine, because of course that will affect the cable length, and also a snaking allowance, which is how much we need to adjust the cable length to cover, like going around sand waves or boulders or anything else that might be down there. The interesting thing is that these algorithms don't actually care about the position of any given thing. They care about the distances between them. So what you input is the lat and long, and then the first stage of the algorithm is to create a distance matrix, which is literally the distance from every position to every other position. So from A13 to B13, from A13 to B12, from A13 to B11, from A12 to B13, from A12 to B12, and so on. And then it will use that information to calculate the results. So what that means is that it doesn't actually have to be a two-dimensional plane, and these algorithms work equally well for three-dimensional meshes, for example, stars in the galaxy. Now, that's all very well, and this is the optimal solution, albeit without T-junctions, which I do not like. I think T-junctions just cause additional maintenance and installation issues, and we shouldn't have them. Yes, you could save a little bit of cable if you went from B5 to A7 and had a T-junction at A7 to A6. Likewise, you could save a little bit of cable if you went from the offshore substation to D3 here at the bottom, and then had a T-junction going to D2 and D1 and D4 and D5. However, in my opinion, for the maintenance benefits of not doing that outweigh the costs of using a cable. What happens, you may ask, if we use 4 loops instead of 8 strings? At the touch of a button with this amazing software that I'm blowing my own trumpet about, you can tell. And in this instance, it goes from 53 kilometers of turbines to 76 kilometers of cable. So from 53 kilometers of cable to 76 kilometers of cable, or nearly 77, there's quite a substantial increase. So you can see that when you go from strings to loops, you do incur quite a big additional amount of cable. And that is why you may say, well, all right, you know, this is just cable length. It doesn't take any account of the actual cross-sectional area of the cable. So although I need an extra 20 kilometers of cable, if I only use a very small cross-sectional area just for back feeding the turbines in the event of failure, then the cost might not be that much. But if you want to actually export anything significant through that interlinked loop, then you are looking at a reasonable amount of extra cost. And this is what accountants see when they do this. Obviously, you can see this isn't totally perfect, because in reality, we don't want cable crossings. And on this chart, there are 3 of them. Now, for reasons I've already described, the code isn't capable of detecting that, and I'm not going to waste the time and effort into making it be able to detect that, because it could be done, but it's not really something I want to spend time on. In reality, we'd just reroute this cable, or we'd suck up a couple of crossings, but certainly we wouldn't be too stressed about it. The main point that I'm trying to make is that the routing matters, and it matters a lot, and that's why these algorithms have been developed. Okay, let's look now at the offshore substation. Here is an offshore substation in this picture on the right. Now, this is Beatrice's offshore substation number 1. Now, they didn't actually call it an offshore substation, they called it an offshore transformer module, because the publicity surrounding it was that it was some super slimmed down device without any superfluous equipment. But I have news for you that most offshore substations are lacking in superfluous equipment, although it is true that the bigger ones do have welfare facilities and workshops and so on. These are significantly expensive components, not just because they're full of expensive electrical equipment, but because they're physically big. They weigh several thousand tons, and then that costs a considerable amount to actually get to location and install. There's 1 or 2 of them per farm. Now, if there's only 1, it is almost always split. By that I mean there's 2 transformers in there, interconnected, but the interconnectors are normally open, and they feed 2 export cables. So it's important that effectively most wind farms are 2 half farms, which allows you to both have power and comms via the fiber optics in the event that something's broken or you need to maintain something. So that's why that is typically done. What they do is they transform the inter-array cable voltage into the export cable voltage, or DC if that's the way it's done, and they also serve as a hub for auxiliary equipment and systems. So, for example, wave monitoring radar, certain meteorological equipment, CCTV hubs, that kind of thing you're typically going to chuck in the general direction of your offshore substation, because it's a good place to put it. Some, especially the big ones far offshore, will also have fairly extensive welfare and repair facilities, so they're actually designed that people can go on them and stay there for a day or 2 in some instances, and all of them have a refuge in case somebody goes on and can't get off, but that's the same with the wind turbines as well. So on modern farms, which are a long way offshore, we're often using HVDC systems now. So what that means is that we will rectify the AC into DC in the offshore platform, high voltage DC, and send that down DC export lines, which have lower losses because of the lack of magnetic fields caused by oscillating current. And then onshore we will invert it and inject it into the grid. So the rectification and inversion equipment is expensive, much more so, but because the losses are lower, you may, in farms which are far away or very large, be able to recoup the losses, and HVDC is a better system for that. But both systems are used in parallel, and mostly we use AC still. The export cables themselves leave the offshore substation, and there's usually at least two of them, and travel below the seafloor, as I say, trenched to about a metre at least below the sand, and then they get pulled through the HDD duct onshore, which is actually what's happening here. The HDD duct will be over there somewhere, and they'll have pulled it through it, and then they'll bring it to the transition joint bay. What we see here is a typical three-phase AC cable. You can see the cross-section of the conductor is here, and this is actually a copper conductor. Now, it's also got the fiber optic cables in two bundles, one bundle here and one bundle here, and it's got this heavy, what looks to be stainless steel armoring on the outside, as well as the final waterproofing layer. So they bring power from the OSS to land, and as I said, they've traditionally been around 220 volts, 220 kilovolts of 50 hertz AC, and occasionally DC now. And they can have copper or aluminium. Again, usually the ones I've seen have been copper, but because copper has increased in price recently, a lot of projects are now going for aluminium. When you buy the cable and you negotiate the price, you typically agree like a bare price or an empty cable price with a supplier, and then they will give you a price based on a specific index that will be agreed once that cable is manufactured for the conductor material, because of course the prices change so much. The weight per meter of the conductor is between about 20 and 50 kilograms per meter per conductor. So these things are pretty chunky. And of course, if you use aluminium, you actually, as I said before, need more by weight, not just by volume. But it's still generally cheaper. As I say, almost always a minimum of 2 export cables. The onshore substation is maybe a little bit less interesting. It's a fairly conventional system. Here's one being built in the north of Scotland for a 1 gigawatt offshore wind farm. You can see it's quite a large unit, but it's not particularly challenging generally. Its job is to take power from the export cables and transform it and condition it into the grid. Now that transforming is fairly straightforward, but the conditioning means dealing with harmonics and reactive power, and that can take up more equipment and more space and more complexity. It will also have the control and monitoring equipment for the wind farm. Now that's generally just a few server racks in a couple of buildings, but it makes more sense to put it in the onshore substation than anywhere else. And from that onshore substation, there'll be various high integrity links to the control room, wherever the control room is, or it could be controlled locally in the event of an emergency. Also, it's going to function as a store and maintenance facility. So for parts that you might not need that often, there'll generally be a big storeroom, and it will have maybe spare switchgear, spare gas, bits of spare cable, spare T connectors, maybe the odd server, PLC, that kind of stuff in there, ready to use, that can be taken to offshore when it's needed. So that's not the operation and maintenance base, but it'll have stores that maybe you don't have room at the operation and maintenance base to have. Now, depending on where your substation is, you have all the usual civil engineering considerations. In Scotland, you do have to worry about water drainage quite a lot. In Taiwan, for example, we have to worry about earthquakes and typhoons. So depending on where you are is going to depend how that onshore substation is created. But as you can see, they are fairly substantial pieces of equipment, but they're a well-known, well-understood piece of equipment as well. As well as transformers, the onshore substation is going to have various equipment for compensating harmonics and reactive power. Now, That equipment may include harmonic filters, reactive power compensators, sometimes known as statcoms, and the exact amount of those is going to depend on the overall wind farm layout. So it's actually going to be one of the final things that are calculated once all the other electrical studies have been done. What are these things for? Well, when we feed into a grid, the grid will give you a thing called a grid code. And what the grid code is a specification for the electricity that you feed into it, especially as a major producer. Now, it's going to tell you things like your harmonic content. It's going to tell you things like your reactive power content and so on. And because of the grid code, that is why the standard of electricity is very, very high. You know, your frequency is very, very reliable, your voltage is reliable, your harmonic levels are reliable, and so on. And that allows people to actually do serious, important stuff with the electricity rather than just hope for the best and plug stuff in. So because the grid code is strict, then filters and reactive power compensation equipment need to be put in the onshore substation because of the amount of switched mode equipment that is in the farm. So the inverters in the turbines, for example, will produce harmonics on the output, and those harmonics will change by the time they get to your onshore. So we will put harmonic filters in the onshore substation. Harmonic filters are RCL circuits, so they're collections of capacitors, inductors and resistors, generally between the grid and ground, and what they'll do is they'll filter out second order, third order and fourth order harmonics and so on up to the standard that is required. Now these are generally passive devices. They don't generally need a lot of input from us, but because of the capacitors they are V. dangerous and are generally put in a special room with controlled access, because those capacitors can have ridiculously high voltages and stored energy. Now, reactive power is a little more different, and that requires a certain amount of active control. So if you remember, we have a power triangle where we have true power along one side and reactive along the other. Then the total amount of power is the volts times the current, but the true power is VI cos theta, and that will always be less than 1 if there is any degree of reactive power in the system. Reactive power occurs when the voltage and the current start to be out of phase. So if this sinusoid here is the voltage, normally the current will be exactly in phase with it, and it might be lower or higher depending on what coordinate system we use, but it will always be in phase. When that current starts to lead or lag the voltage, then we get a situation where we have reactive power. And reactive power is not good for a load of reasons, but the main two reasons that it's not good is, one, because the reactive power increases theta, then cos theta is dropping, therefore the amount of real power we can get out of the system is lower than it would otherwise be when we have reactive power. Secondly, the current for a given amount of actual real power needs to be higher than it would otherwise be, and that current is flowing through the same conductors, and because the current flow is higher than it would otherwise be, the losses due to that current flow are higher than they would otherwise be. So reactive power, not good, don't like it. Luckily, we can use switch mode systems, so collections of GTO thyristors, or more recently IGBTs, actively switching RCL circuits, and they can add or remove reactive power as is appropriate to the system. Again, these devices are quite large, they're quite expensive, and they have a lot of very high voltage stored energy in them, so they have to be treated with the utmost care. Usually you're going to design more of these than you think you're going to need. so that you've got additional ability to handle reactive power and harmonics. And in some instances, you may be able to get a little bit more money from the grid by offering to provide reactive power compensation services to other industries nearby that may require it. Unfortunately for me, this whole area of engineering is not something that I am an expert on, so I can't really give you any more information than I already have done on that. Finally, finally, I want to look at high voltage switchgear. Now, what the switchgear is it's the devices that allow power to travel from the source to where it's needed. So if I, again, draw your turbine, that's going to have a switchgear in it, and that switchgear is going to go to the inter-array cable. Then that is going to go into the offshore substation, where it will have another switchgear. Then that will go through a transformer, where it will go to a higher voltage piece of switchgear, and that will go through the export cable to onshore, where it will go through another piece of switchgear, and then it will go through the onshore transformer, and then it will go through at least one, but probably more likely two pieces of switchgear before it connects to the grid. So from the turbine, you've got 1, 2, 3, 4, 5, and probably 6 pieces of switchgear between the turbine and the grid. Now, each one of those pieces of switchgear is going to be handling between 33 and 400 kilovolts, depending on where it is and what the grid facilities are. What switchgear does is it allows you to open and close electricity. Now, the most important thing there is open. Its main purpose is to be able to open in the event of a fault. So this high voltage switchgear is very specialist equipment that can open at full fault current. So regardless of whether you short circuit the current, the switchgear must be able to open. And it does that using a mechanical system based on springs. So these are not relays, they are very heavy duty clockwork machines that operate on springs such that the switchgear can open no matter what, and it must be able to do that. Now, the signal to tell it to open or close comes from a device called a protection relay, which is a confusing name because it's not like a solenoid type relay. It's a little computer, and what that computer does is it receives instructions from the main control system, and it also monitors the condition of the electricity going in and out of that switchgear. If it is ordered to close the switchgear, it can do that. If it needs to open the switchgear for whatever reason, it will do that. And the way it opens the switchgear is usually there's one solenoid in the switchgear that when it opens, it moves a physical mechanical latch which allows the opening switchgear to spring in, and there'll be a bang and the switchgear will open. Now, because of the high voltages involved and because of the relative lack of space inside the wind turbine and the offshore substation, typically gas insulated switchgear is used. Now that gas is there to quench the arc that occurs when very high voltage contacts are brought together and pulled apart. In principle, you could use vacuum switchgear, which is widely used in the grid, for example. After all, vacuum is a better arc quencher, but for various reasons to do with compactness, that's generally not possible on wind farms. Therefore, we use gas insulated switchgear, and the gas is sulfur hexafluoride, which is commonly known as SF6. Now, the bad thing about SF6 is that it's got a global warming potential which is 23,500 times higher than carbon dioxide, and it lives in the air for about 3,500 years. Now, because we live in a very sensationalist society, you know, you're going to see little news articles pop up saying, you know, wind farms filthy secret SF6 and so on, and it's like, because we use SF6, you know, it totally negates the entire purpose of having a wind farm, as if A, the amount of SF6 that we use is in any way comparable to the emissions that we save, and B, as if we just routinely leak it out into the environment. Because of course we don't, but still more leaks out than I would like. I'm estimating probably up to 1% of it may need to go over sort of a 25-year lifespan of switchgear. Now that's more than I would like, and it's more than anyone else would like either. Therefore, significant efforts are underway to reduce and replace SF6. Notwithstanding that, it's still worth noting that the global warming potential caused by leaking SF6 is considered to be about 0.001% of the emissions saved by using wind turbines in the first place. So in comparison to the benefits of having a wind farm from a CO2 and global warming point of view, the SF6 is not even a significant factor, but it is nonetheless one of the factors that is being looked at, because believe it or not, in this industry we do take it seriously. There's a lot of industries that don't, but we do. So in the next few years we will remove SF6 completely from new builds, but it's worth noting that these things last a long time, so there will still be SF6 in switchgear for probably 20 to 30 years. I'm not going to say a lot about the control system. Reason being, control systems are bespoke to the wind farm. Okay, so every wind farm has its own specific control system. The wind turbines themselves, they will have their own PLC, and that PLC typically just controls that wind farm, pardon me, that turbine. And what it will do is it will yaw that turbine, it will pitch that turbine, and it will create any fault codes for that turbine. That's about all it'll do. In the event that it needs to open the supply breaker for that turbine, it's also capable of sending a signal into that supply breaker to do that. Generally though, that PLC in that turbine is concerned with that turbine and maximising the power output of that turbine. There is a high voltage control system. This is the highest integrity control system on the farm, and this is the only system which is allowed to close HV breakers. Several systems can interact with the HV breaker protection relay in order to open them, so the PLC on the wind turbine is one of them. But the high voltage control system is the only one that is permitted to close those breakers again. It is the highest safety integrity system on the wind farm, and it has to conform to some very, very high standards of reliability, because the consequences of getting it wrong are generally less than ideal. There's a wind farm park control system. So this is different from the individual wind turbine control system. The wind turbine control system is only responsible for that turbine. The wind farm park control system controls the park as a whole, monitors the park as a whole, and if a curtailment request is required, it will send individual instructions to the relevant turbines to reduce production. In practice, as I said in part one of this presentation, curtailment is extremely rare. It very rarely happens, and again, all these Daily Mail fanaticists who are complaining about wind turbines shutting down when it's too windy, 99% of the time is not true. There's a balance of plant control system. This controls all the auxiliary equipment, so sewage treatment plants, water pumps, drainage systems, closed circuit televisions, wave radar, bird radar, navigation lights, and so on. All of these systems go through the telecoms system. Now that telecoms system is the fibre optic that we saw in the cables, but also generally there's some kind of LTE, so 4G network, or some booster system or satellite backup system that will allow us at least a minimum amount of control in the event that the export cables are knocked out. Most wind farms have a control room at the maintenance port, but this is not strictly necessary. So because these are computer-based systems, we can, and we do, control them from everywhere. So for example, each wind turbine will feed back to its manufacturer. So Vestas, for example, will sit in an office in Denmark and monitor every single one of the tens of thousands of turbines that they have in operation around the world, and they will probably tell the operator if there's a problem. Likewise, if there's curtailment requests, it might be the central grid, depending on the integration system, it might be the central grid that actually makes that request and does it without anyone else knowing about it. It really does depend on where you are and what system you have as to what you get. Of interesting importance to these things that I didn't realise until recently was the importance of GPS antennas for the purposes of synchronization timing of multiple systems. And this was something I hadn't appreciated. GPS, of course, is predominantly a time-based system. The reason that we can build GPS satellites now is because we have the ability to make very small spaceborne atomic clocks. Those signals are used for so much more than positioning, and this was a whole factor that I hadn't really thought that much about until recently, which does give me additional concern, given the instability of the world recently, that there may be a range of unfortunate consequences from GPS jamming, for example, that I hadn't necessarily considered. That would take a software guide to tell you more about that, though. In addition, the links that go to the turbines are generally doubled up into loops. Now, of course, they may still have to be in the same physical inter-array cable if you've only got a string topology, but at least you've got more than one bunch of fiber optics leading there. At the moment, I don't know of any farms that have wireless connections to the control systems on the farm, but I suspect that that may become more common in future. Either way, the control systems are bespoke to that farm. If we look at some future developments, what we might see, we're going to see the increasing use of high voltage DC for sure. The reason, as I said, is that we've developed all the easy wind farms now. All the ones that are close to shore, they've been done. All the ones that are in shallow water, they've been done. We're having to go further away. If we go further away, then the electrical losses in the export cable become a bigger factor. And because of that, we need to have HVDC. We are going to see increasing use of 66 kilovolt inter-array cables and maybe even higher voltage. I mean, now we've got turbines in the 15 megawatt class being specified for farms. So within 5 years, we'll see 20 megawatts, then we're going to see 25, maybe even 30 megawatt turbines. They may need higher voltage. It is foreseeable that we may use HVDC directly from the turbine. I don't know about that, but we may see that. We may see things like shared offshore infrastructure, including substations. For example, we may build one large artificial island somewhere and then channel a wide range of individual floating or fixed wind farms into that substation so that we can take advantage of economies of scale. We are already seeing replacements for SF6 and they're hitting the market already, so it won't be long before SF6 is completely void on wind farms, but there still is SF6 there today. And we're going to see a wide range of specific solutions for floating wind farms. Now, floating wind farms are a bit overhyped at the moment, in my opinion. Like, a lot of people are talking about them. Nobody really knows how to build them, but they will, and it will be standardized within sort of 10 years. So we may see things like submerged substations, perhaps for cooling. We may see special dynamic cables. We've got to have certain maintenance facilities for them. You know, in principle, you'll be able to tow the turbine in to fix it, for example, which, you know, I'm not sure that that's ever going to be economically beneficial, but it might be versus having a jack-up vessel. I don't know. So we're going to see a range of solutions which are specific for floating farms. We will also see increasing deployment of small-scale energy storage using batteries. Now, energy storage, grid energy storage, is something that I would like to do a whole separate talk on, because it is, and has been for a very long time, the elephant in the room of renewable energy. Because the first argument that an anti-renewable energy person is going to make is, what do you do when the wind doesn't blow or the tide doesn't pull or whatever? It's not an unreasonable argument, The answer up until now has been if we build enough wind, if we build enough solar, if we build enough hydro, then there'll always be some somewhere. That's part of the answer. And the second part of the answer has been we're not completely replacing fossils on the grid, therefore there's always something there. Now, unfortunately, as we build more and more renewables, we absolutely are replacing fossils on the grid. Therefore, we need to have a reliable power supply. At the moment, that reliable power supply is being relied, if you like, that's not the appropriate verb, but you get my point, by interconnectors on the grounds that if we interconnect grids over a wide area, then there will always be renewable energy somewhere. Now, that's not entirely unreasonable, but eventually we're going to need very large scale energy storage. Small scale energy storage, however, is for more local reasons of control and maintenance, and that is definitely going to get bigger. In addition, we may see things like synthetic inertia systems needed, because with the shutting down of large rotating mass fossil fuel plants, we don't get the inertia in the frequency stability range that we need. So synthetic inertia relying on some sort of stored energy is also going to be a thing that happens in the future. In summary, what have we learned in part 4? We've learned that the largely unseen networks of cables, switchgear and transformers is vital to making a wind turbine useful. So without this network, a wind turbine is an expensive sculpture. The layout and design of the electrical system has a significant influence on the overall economy of the wind farm. So if we get it wrong, it costs a lot more, and we put quite a lot of effort into trying not to make that happen. And trends are towards higher voltages, DC export and SF6 free switchgear. Those are the trends that we see. Later, in the final part of this presentation, we're going to cover the construction, operation and maintenance of the wind farm. So, as usual, I'd like to thank you very much for your attention during this presentation. If you've got any comments or questions, feel free to throw them in the general direction of the box below. And have a lovely day. I'll catch you on the flip side for the next presentation. Take care.